you can start. Thanks.
Okay, hi everyone. So my name is Oleg and I'm from Grappa in Amsterdam, and I'm going to tell you about recent work that we've been doing with my colleagues Guillermo and Christoph about reconstruction of cosmological initial conditions. So as it already has been emphasized many times here, it is a very important problem because these initial conditions contain the maximal possible amount of information about our particular realization of the universe. But the main challenge here is that this problem requires dealing with a super huge multi-million dimensional parameter space, and so there has been a lot of approaches proposed to deal with this, like the Borg project, which relies on Hamiltonian Monte Carlo. But the problem with these classical approaches is that they require you to write down the likelihood, they require your simulator to be differentiable, and they are usually very slow. And with the recent progress in machine learning, there is a lot of interest in trying to apply these new methods to this problem, like the recent work with diffusion models, for example. But here I want to talk about an approach developed in our group, which is a sequential autoregressive neural ratio estimation implemented in a package Swift. And so the main advantages of our work is that it is likelihood-free, so it works with any non-differentiable simulator, and it's very fast and flexible. Yeah, so there are two main ingredients to our method. The first one is that it is sequential, which means that we perform training in a series of rounds, and each next round is training data for next round is samples from the tempered posterior from the previous round. And the second part is autoregressive modeling, which means that in order to deal with a very complex mapping between the initial and final field, we do the embedding in latent space using embedding networks such as UNets or GNNs. And in this latent space, we can model the relationship between initial and final fields in an autoregressive Gaussian way, which means that each next pixel depends on the series of previous pixels. And so we see that our approach works for 3D boxes, and our next goal is to train it for the highest resolution boxes that we deal with. And so stay tuned to updates from our part. Thank you.
Thanks, Oleg.